Hey, welcome to my channel Industry 4.0. Today, in this video, you will learn about IoT software source, IoT operating systems, IoT protocols and IoT applications in detail. Please like and share the video and subscribe to my channel. So, let's start. Introduction. Today, Internet technology allows the communication of just about all kinds of devices, like sensors or maybe appliances. We, normally speaking, need operating systems, protocols, applications, and platforms to assist these structures. This can be briefly described during this post to satisfy the wants needed for every specific problem. IoT Operating Systems. Windows Developer Program for IoT is designed by O'Reilly Solid and Microsoft Build. This program allows users to run a version of Windows on the Intel Galileo board for both makers and Windows developers to get into the IoT space. Some OSs could also be mentioned here as examples. Contiki OS for the IoT is an open-source OS for memory-efficient networked embedded systems and wireless sensor networks that give IP communication, both for IPv4 and IPv6. This OS is described during a study presenting the low-power constrained application protocol (CoAP) implementation for Contiki that leverages a generic radio duty cycling mechanism to realize high energy efficiency, such as distributed real-time control systems (DRCS). Representational state transfer (REST) may be a co-coordinated set of architectural constraints that attempts to attenuate latency and network communication while at an equivalent time maximizing the independence and scalability of component implementations. REST permits the caching and reuse of interactions, vibrant substitutability of components, and processing of actions by intermediaries. This is for thereby meeting the requirements of an online-scale, distributed hypermedia. The goal of REST is to realize this in a more lightweight and simpler manner seamlessly integrated to the online. Friendly OSs for IoT, RIOTs, use URIs for encapsulating and identifying services on the RIOT. RIOT can be a standard C and C++ programming OS that explicitly considers devices with minimal resources, provides multi-threading, also has real-time capabilities, and wishes only a minimum of 1.5 KB of RAM. As mentioned within the reinvented RIOTs will add improved scalability, connectivity, security, safety, and an extended feature set to the solid real-time performance, low latency, and multi-core processor support of the RIOTs of today. Additionally, to the above mentioned, there are many OSs designed especially for IoT like ARMOS, SparkOS, and TinyOS. IoT Protocols. In this subsection, we mention a number of the most methods associated with protocols for developing IoT technologies below. Service-oriented architecture, SOA, may be a loosely coupled architecture designed to satisfy the business needs of organizations. An SOA doesn't necessarily require the utilization of web services, but these are, for many organizations, the only approach for implementing a loosely coupled architecture, especially for sensor and device functionality. SOA was primarily for connecting complex and static enterprise services because web service development has not always been an easy task. Since sensors and devices have limited resources like computing, like communication and storage capabilities, this architecture requires simplification, adaptation, and optimization for appropriate performance. Authors propose an information-centric session mechanism to explain service behavior working upon distributed events called event session. Another study shows an SOA-based real-time service bus model which may be wont to support constructing web. Over the last decades, the Web Protocol version 4, IPv4, has emerged because of the mainstream protocol for the networking layer. However, this protocol wasn't designed for the IoT capabilities because it's inherently limited to about 4 billion addresses. With the emergence of Internet Protocol version 6, IPv6, it scaled up the web to an almost unlimited number of worldwide reachable addresses. IPv6 provides 2,128 unique Internet addresses, or 3.4 by 1038 addresses, which corresponds to over 6.67 by 1017 unique addresses per square millimeters of Earth surface. Within the analyze the suitability of various IPv6 addressing strategies for nodes, gateways, and various network access deployment scenarios within the IoT applications. It has become evident that social networks are important platforms that allow people to share information and communicate for achieving different objectives. Therein sense and within the IoT world, Gui et al. Have proposed a tool that permits information sharing and dissemination within/among opportunistic communities that are formed with the movement and opportunistic contact nature of humans. Atsori et al. Propose to use this kind of social relationship introduces a communication framework among devices and sensors within the IoT world called IoT Paradigm, Social IoT. Another area to be stated here is healthcare. Healthcare may be a relevant area where IoT can help in a significant way thanks to several devices and sensors that allow monitoring and controlling diseases with low cost. In their study, Bui and Zorzi explain issues related to IoT protocols and the requirement for being an appropriate technology for healthcare. Does et al. In explain the building of infrastructure for controlling and monitoring biological signals reception and little clinics through mobile healthcare devices and smartphones. In another study, they propose a way to enhance accessibility to IoT data resources and IoT-based systems for emergency medical services to demonstrate the way to collect, integrate, and interoperate IoT data flexibly so as to supply support to emergency medical services. In business, within the area of supply chains and retail, any improvement is often helpful since these businesses are multi-billionaire industries, and a touch positive change can impact during a drastic way in revenues and costs. Within the authors briefly discuss how IoT can have an impact on the commercial processes and provide chains and their future perspectives. There also are some proposals for the latest technologies for pedigree devices in food safety. The most objective is to trace the processes in production, storage, transportation, sale, and even using phases of foods. In this study, they presented several technologies that combat phony products within the global supply chain. Some other applications like Li et al. Have designed an agricultural production system for monitoring and analyzing harvest statistics. The goal is to require smarter decision-supported information from sensors in farms. If they suggest a replacement schema for applying the IoT on intelligent traffic systems.